Hi everyone, welcome to lecture 23 on probability and causality. The objectives for this video are the following, so after watching everyone should be able to, number 1, derive the odds form of Bayes' theorem. Number 2, calculate posterior odds using the odds form of Bayes' theorem. And number 3, interpret the posterior odds as evidence of a certain degree of strength. Okay, a heads up before we get going. The corresponding section in the text to this video is relatively short, but I want to spell it out slowly and patiently because I think it's an important section and there's a ton of application with this material, so we're going to deviate from the book a little bit here, but I think it will be useful and interesting to see. So let's recap our journey over the past few weeks. We started in chapter 5 by turning to this idea of causality, or cause and effect, and asking what do we mean when we use this term. In particular, we gave one analysis of causality. We analysed it in terms of necessary and sufficient conditions. That is, the suggestion from chapter 5 is that sometimes what we mean when we say something like X causes Y is that X is a sufficient condition for Y, or X is a necessary condition for Y. However, while talking in terms of necessary and sufficient conditions can sometimes explain what we mean, when we say things like X causes Y, there are also instances where we use the term causes, where necessary and sufficient conditions can't fully capture what we mean. Here's one: smoking causes lung cancer. Analysing this use of the word causes in terms of necessary and sufficient conditions can't fully capture what we mean. For example, we can't mean smoking is a sufficient condition for lung cancer because some people smoke and never contract lung cancer. And on the other hand, we can't mean smoking is a necessary condition for lung cancer because some people who never smoke nonetheless contract lung cancer. So there's something more going on when we say smoking causes lung cancer. And the point of this video is to fit probability into this analysis we're giving of the word causality. And instances of the term causality like this one, smoking causes lung cancer, is where probability fits into this analysis. So this will round off chapter 6 by linking together two of the big notions we've been talking about, probability and causality. And in particular, we're going to show how probability fits into this picture when we analyse this term causality. So how does probability fit in here? Well, when we say something like smoking causes lung cancer, what we mean is something probabilistic, that if you smoke, you are more likely to develop cancer, or your chances of developing lung cancer are higher. So you ask, well, what does this more likely mean? Now, one way of interpreting this is to say that X is good evidence for Y. And it turns out, using our ideas of probability, we can actually quantify this idea of evidence. So this is where our analysis of causality is going to take us. We're going to quantify the degree to which an observation can be called evidence for some hypothesis. So let's see how we do that. And like I said, this is a departure from the book, but I think it's interesting. It's applied absolutely everywhere in the real world, and it's a nice consequence of our work on Bayes' theorem. So I think it's worth spending some time going through here. So first, let's recall Bayes' theorem, which when we met it originally appeared in this form. So P and Q are statements with non-zero probability. Then the probability of Q given P is the probability of P given Q times the probability of Q, all divided by the probability of P given Q times the probability of Q, plus the probability of P given not Q times the probability of not Q. Now, I ask you to prove in assignment 8 that an equivalent form of Bayes' theorem is this, which says the probability of Q given P equals the probability of P given Q times the probability of Q, all divided by the probability of P. So this is just Bayes' theorem in another form. I will leave the proof to the assignments and we'll skip over it here. Now let's do some scribbling and copy this form of the theorem up. Now because this works for any two statements P and Q, We can also replace Q here with not Q. And if we do that, this version of Bayes' theorem tells us this, that the probability of not Q given P equals the probability of P given not Q times the probability of not Q, all divided by the probability of P. Now let's call these two equations 1 and 2. Now let's consider the ratio of the left-hand sides of equations 1 and 2. And all I mean by ratio is it's the left-hand side of equation 1 divided by the left-hand side of equation 2. Then this thing, P of Q given P over P of not Q given P by equations 1 and 2 is equal to the ratio of the right-hand sides of these equations, which is P of P given Q times P of Q times P of P, all divided by P of P given not Q times P of not Q times P of P. That's what we get when we divide the right-hand side of equation 1 by the right-hand side of equation 2. Now these P of P's cancel, and so what we end up with is this. P of Q given P over P of not Q given P equals P of P given Q times P of Q over P of P given not Q times P of not Q. And this thing is what we call the odds form of Bayes' theorem. So let me explain what we're seeing here. Let's look back at Bayes' theorem for a second, so up at the top here, and let's label some terms. So we've got Q and not Q appearing in these theorems. We call Q and not Q hypotheses, and we call P the evidence. We call the probability of Q given P the posterior on Q, and similarly we call the probability of not Q given P the posterior on not Q. We call the probability of P given Q the likelihood of P given Q, and similarly we call the probability of P given not Q the likelihood of P given not Q. We call the probability of Q the prior on Q, and similarly we call the probability of not Q the prior on not Q. Now there's nothing substantial going on here, we are just naming these terms in Bayes' theorem so that we can gain a better intuitive understanding of what's going on here. So when we look back at the odds form of Bayes' theorem, which we've just derived, what we've got is this. The left-hand side is the ratio of the posterior probabilities on Q and not Q respectively. This ratio is also sometimes called the posterior odds in favour of Q. It's in favour of Q because it's in favour of whichever hypothesis is involved in the numerator, so in the top part of this ratio, and here that is Q. This term, P of P given Q over P of P given not Q, is the ratio of the likelihoods. This we call the Bayes factor. And this term, the last one, P of Q over P of not Q, is the ratio of our priors, sometimes called the prior odds in favour of Q, and again it's in favour of Q because it's in favour of whatever is involved in the numerator or the top part of the ratio, and here that's Q. So we've got these three terms labelled. We've got the posterior odds on the left, we've got the Bayes factor, and we've got the prior odds on the right. Now the point of doing all this is that we're interested in making precise sense of the degree to which some observation is evidence for a hypothesis. And the way we've labelled terms, we've got evidence and hypotheses in play now. So let's take our smoking example. We're interested in the degree to which cancer is evidence that someone is a smoker or not. So what we're interested in is the probability that one smokes, given that one has developed lung cancer, compared to the probability that one does not smoke, given that one has developed lung cancer. So let's look at what we've got. Smokes is one of our hypotheses. Let's write hypothesis 1. And does not smoke is the other one. And this one is usually called the null hypothesis because it hypothesizes no effect, so you don't smoke despite the fact that you've developed lung cancer. Now the evidence here is that one has developed lung cancer. and we're trying to quantify the degree to which lung cancer can be described as evidence for someone's being a smoker or not. To do this, we construct a table recording all the relevant information, and we use the odds form of Bayes' theorem, which we've derived above. Now, the table is very simple, you'll be glad to know. It starts like this. First, we record our hypotheses. They are, in this case, hypothesis 1, which is smokes, and the null hypothesis, does not smoke. The next thing we do is record the priors and the likelihoods for each hypothesis. So we record the prior on hypothesis 1, which, looking back at how we've defined this, is the probability that one smokes, and according to some statistics I looked up, the probability of any individual being a smoker is around 0.21. So our prior on hypothesis 1, or our prior on being a smoker, is 0.21. And so our prior on the null hypothesis, or our prior on someone's not being a smoker, is the probability that one doesn't smoke, which is 1 minus 0.21, which gives you 0.79. Now let's look at the likelihoods. The first one we're interested in is the likelihood that one develops lung cancer given hypothesis 1. So the likelihood that one develops lung cancer given that one smokes. And according to the same statistics, the probability that one develops lung cancer given that they smoke is around 0.00427. The second likelihood we're interested in is the likelihood that one develops lung cancer given the null hypothesis, so the likelihood that one develops lung cancer given that one does not smoke, and according to statistics, the probability that one develops lung cancer given that they don't smoke is around 0.00013. Now we look back at the odds form of Bayes' theorem and we do what it tells us. So our table is complete at this point. That's all we have to do. Now the odds form of Bayes' theorem tells us that the posterior odds in favour of hypothesis 1, or the ratio of the posteriors in favour of hypothesis 1, is equal to the prior odds in favour of hypothesis 1, or the ratio of the priors in favour of hypothesis 1, times the Bayes factor, or the ratio of the likelihoods in favour of hypothesis 1. And we have all the priors, and we have all the likelihoods. That's what we've just filled in the table. So we can go ahead and simply calculate those ratios. So let's do the prior odds in favour of hypothesis 1 first. Here, the prior odds in favour of hypothesis 1 is the prior of hypothesis 1, so the probability that one smokes, divided by the prior of the null hypothesis, so divided by the probability that one doesn't smoke. So this is just 0.21 divided by 0.79, which is around 0.27. Next, let's look at the Bayes factor, or the ratio of the likelihoods in favour of hypothesis 1. The likelihood that one develops lung cancer given that one smokes is 0.00427, and the likelihood that one develops lung cancer given that one doesn't smoke is 0.00013. So 0.00427 divided by 0.00013 gives you an answer of around 33. And so, by the odds form of Bayes' theorem, the posterior odds in favour of hypothesis 1 is the prior odds in favour of hypothesis 1 times the Bayes factor, which in this case is 0.27 times 33, which gives you around 9. And this number, the posterior odds in favour of hypothesis 1, which was that someone is a smoker, and this number, the posterior odds in favour of hypothesis 1, remember, was that someone is a smoker, tells us that given someone has developed lung cancer, they are 9 times more likely to be a smoker than to not be a smoker. So this is how you interpret the posterior odds, saying what this number means here. And it's this number, 33, the Bayes factor, which quantifies the degree to which having developed lung cancer is evidence that one is a smoker, because the Bayes factor tells you how much your prior odds should shift when you update. Now, to complete this little survey, in the literature, people have attempted to describe how we should interpret different values of the Bayes factor. So here is one of those descriptions. We'll say a Bayes factor of 1 to 3 is negligible evidence. A Bayes factor of 3 to 20 is positive evidence. A Bayes factor of 20 to 150 is strong evidence, and anything above that is very strong evidence. So in this example, we'd conclude that having developed lung cancer is strong evidence that one is a smoker because our Bayes factor was 33. Okay, so we've seen how we can quantify the degree to which an observation can be called evidence for a hypothesis compared to a null hypothesis. I want to finish here by talking a little bit about what's mentioned in the book and how that fits into the bigger picture that we've described here. Now, in the book, the section on probability and causality starts by suggesting a couple of definitions. In particular, he makes this definition. We say that P has a tendency in the direction of sufficientness of Q, just in case the probability of Q given P is greater than the probability of Q given not P. So a little bit wordy, but we'll unpack what it means. And we also say that P has a tendency in the direction of necessariness for Q, just in case the probability of P given Q is bigger than the probability of P given not Q. Now, the first thing to notice is that we can divide both sides of the first inequality, so in definition 1, by P of Q given not P. And if we do that, we obtain equivalently to definition 1, P has a tendency in the direction of sufficientness of Q, just in case the probability of Q given P over the probability of Q given not P is greater than 1. And similarly, we can divide both sides of the inequality in definition 2 by P of P given not Q, and doing that we obtain equivalently to definition 2. P has a tendency in the direction of necessariness for Q, just in case the probability of P given Q over the probability of P given not Q is greater than 1. Now, we think back to the odds form of Bayes' theorem. If we think of P as our hypothesis and Q as the evidence, then the odds form of Bayes' theorem said this: P of P given Q over P of not P given Q equals the Bayes factor times the ratio of the priors, so equals P of Q given P over P of Q given not P times P of P over P of not P. So if we compare the Bayes factor here to the definition of tending in the direction of sufficientness, which is what's in the book, we see that the inequality in the definition is satisfied just in case the Bayes factor, when P is our hypothesis and Q is our evidence, is greater than 1. That's why the book suggests this definition. The inequality in the definition of tending towards the direction of sufficientness is satisfied just in case your Bayes factor is greater than 1 here, so just in case your evidence carries some sort of weight, even if, by what we said before, it's only very weak. And similarly, if we think instead of Q as our hypothesis and P as our evidence, then the odds form of Bayes' theorem told us this: P of Q given P over P of not Q given P equals the Bayes factor times the ratio of the priors, so equals P of P given Q over P of P given not Q times P of Q over P of not Q. So if we compare the Bayes factor here to the definition of tending in the direction of necessariness this time, we see that the inequality in the definition is satisfied just in case the Bayes factor, when Q is our hypothesis and P is our evidence, is greater than 1. And that's why the book suggests this definition. The inequality in the definition of tending towards the direction of necessariness is satisfied just in case your Bayes factor is greater than 1 here, so just in case, again, your evidence carries some sort of weight, Again, even if, by what we said before, it's only very weak weight. Okay, so one last disclaimer before we wrap up. One has to be careful here when you carry out this Bayesian analysis with what you conclude at the end of it. What we've been interested in here is the degree to which one might call developing lung cancer evidence for one's being a smoker. We established that one is much more likely to have smoked than not smoked, given that that person developed lung cancer. This positive statistical relevance that we've established doesn't quite warrant saying we've established a causal relationship here. For example, suppose that smoking itself didn't cause the cancer, but that desire to smoke and cancer were both effects of some underlying biological condition. Then the biological condition is a confounding variable here, so smoking would still be statistically positively relevant to cancer, but as a symptom of having something like a certain gene rather than a cause of cancer. So to really establish causal relationships using the analysis we've given here, you have to control all the variables that might confound your study and make sure they're all fixed while you manipulate the variable that you're interested in. So to do better than we did here, you would want to compare the probabilities that one smokes, given that they developed lung cancer and holding all other variables fixed, to the probability that one did not smoke, given that they developed lung cancer and all other variables are fixed. Determining what constellation of factors to hold fixed, of course, is a tricky business, and this is why establishing causal relationships is quite a delicate affair in science. Okay, that's all I'm going to say on that matter. So with that, we'll conclude Chapter 6. Next time, we'll move into Chapter 7, which looks at different kinds of probability. So have a go at your self-reflection questions, and I'll see you all next time.